All right, guys, I also want to look at some solutions to some just straight counting and basic probability. Going back, you know, when we started this whole probability section, we originally started by looking just at counting, because at the end of the day, probability is all about counting the number of ways something can happen over the number of all possible outcomes. So let's revisit an old review here and see what we can come up with. And actually, before I do, I want to mention that I'm not going to show my computations, okay? I have different classes. Some are using Excel, some are using the TI 83 or 84. So you're going to see my setup, and you're going to see my answers. You're not going to necessarily see the mechanics of plugging things into either computational tool, okay? So that's something that you should be comfortable with on your own, especially by this point. So when you see numbers appear, just know I've gone to one of those two places to get them. Okay, so having said that, let's hop over here and look at this counting practice. So how many different passwords are possible if the password has 4 letters and 3 digits? So 4 letters, 3 digits, repeats are allowed, okay? And so we have, if you think about what the password would look like, this is the fundamental counting principle, right? The number of ways that all 7 of these things can occur is the number of ways they can occur individually, all multiplied. It's that product. So 4 letters, well, we're assuming the English alphabet. So there are 26 choices. Repeats are allowed, so every time we pick a letter, right, because we're going to have 4 letters followed by 3 digits, you got 26 options. And then digits, right? There are 10 possible digits, 0 through 9. And so what do you do with these? Well, you multiply them together, okay? And that might be a little easier if we think of this as 26 to the 4th times 10 to the 3rd. Let's see what we get. Let's see here, 26 to the 4th times 10 to the 3rd. So we get 456,976,000 different possible passwords. Okay, number 2. A landscaper needs to plant 4 oak trees, 8 maple trees, and 6 poplar trees, evenly spaced along a border of a lawn. How many distinguishable arrangements are there? So when I say distinguishable arrangements, I'm mentioning that, right, I can't tell which oak is which. I can't tell which maple is which, or which poplar is which. So if you remember, we had this nice little formula here, all the way up to nk factorial. And so what I want to notice is that there are how many objects total? Well, 4 plus 8 is what? 12 plus 6 is 18. So there are 18 total objects, and then the repeats. 4 oaks, 8 maples, 6 poplars. And let's see what we get for that. So 18 divided by, then 4 factorial. Oops. Four factorial times 8 factorial times 6 factorial. And so I'm getting, I'm gonna just verify this real quick. I'm getting 9,189,180. Okay. All right, number 3, you own 3 horses in a 12-horse race. What is the probability that your horses finish first, second, and third? All right, there's actually 2 ways to do this. We can look at this from a permutation perspective or a combination perspective. All right, so we want to look at this, right? Remember, we're counting, right? So the number of ways your horses can finish first, second, third, divided by all possible first, second, third finishes. Okay? So the probability that your horses go 1, 2, 3. Well, let's think about this. If I'm thinking about this from a permutation perspective, I might see this as, well, I have 3 horses that could get first, then 2 that could get second, and then 1 that could get third, right? So that's 3 factorial divided by, and then we have 12 horses in the race, 12p3. That would be all possible 3-horse finishes, okay? And so that's going to be 6 divided by, and then what do we have here? 12p3. Oops, 6 divided by 12p3. So we're getting 0.0045. There's another way to look at this. Do I really care which one of my horses finishes first, second, and third? Or do I just care that my horses finish in first, second, and third? From that perspective, I have a combination. And there's only one combination I care about, my 3 horses. And then my denominator then would be 12C3, all different combinations of first, second, third finishes. And guess what? You get the same thing, okay? So 2 different perspectives. You got a permutation perspective, which honestly I think is the more natural way to think about this problem. But over here, you also have the combination perspective, okay? All right, number 4. Popular magnet school admits most of its students based on a lottery system. If 500 applicants are vying to fill 30 spots in a kindergarten class, how many different kindergarten classes are possible? Well, let me ask you this. Does the order of selection matter? Well, think about it this way. Picture being in a physical classroom, and we're all sitting in a seat. And we all stand up and change our seats. Is this now a new class, or is it the same class? Yeah, it's the same class. So the order doesn't really matter, which makes this a combination, okay? And so 500 choose 30. Which is 1 point. Now I'm going to round here. 1.45 times 10 to the 48th. I mean, really? And this is a perfectly legitimate answer right here. But based on what your computational tool is, you might see this. Uh-oh.
What happened?
Hold on. 500. I lost it here. Let's see. 30. So 14452 595, and then 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. You'll have 48 of those. Astronomical number. Okay, very, very big. All right. Number 5, state lottery. Players choose 5 numbers out of 40. A player wins if all 5 numbers are chosen regardless of order. Regardless of order tells me this is a combination. What is the probability that a person has a winning ticket? Well, let's go back to counting. How many winning tickets are there? There's only one. And then how many different combinations of 5 numbers are there out of 40? Well, I have no idea what that is. That's a raw number, but I do know that I can figure it out by computing 40C5. So let's do it. 1 divided by 40C5. And so we get, let me see here, 40C5. 1 divided by that. We get 0.
Wait, that's
6. 1, 2, 3, 4, 5, 6. Wait, sorry, I'm counting again. 1, 2, 3, 4, 5. 5 zeros. 15197. A tiny number. You might call it 1.5 times 10 to the negative 1, 2, 3, 4, 5, 6. Okay. All right. Number 6. All right. So here we have results from a polygraph test. And as you probably know, they're not admissible in court. There's a reason for it. We're about to find out. So the way this is read, you have a positive test result. Now from these positive test results, how many were there? Well, 15 plus 42. So there were 57 of them. 15 did not lie. 42 did lie. Now remember, a positive test result, it indicates lying, okay? Negative test result, well, there were how many total? 41. Notice, some of the people that got a result saying they lied did not lie. And similarly, some of those who were told they did not lie according to the test actually did lie. So what we want to do is compute these. So a negative test result given lying. That's this first one. Now remember what that is. This is conditional. This means that I'm looking only at these 51 liars. And of the 51 liars, how many had a negative test result? Yeah, 9. Okay, so 9 over 51, which is approximately 0.1765. Now we can also compute this conditional probability. Lie given negative test result. Well, now my vision is just out of, change colors here, these negative test results, right? That's my denominator. There are 41 negative test results. How many of those did not lie? Well, 9. And what do we get? Well, in this case, 0.2195. So think about what this is saying. This is saying that if you're lying, you can get a negative test result almost 18% of the time. And of all the negative test results, about 22% of those will actually be from liars. The test is horrible. It is incredibly inaccurate. And the only place you might see it is, well, you can imagine, a place like, I don't know, Maury Povich or any other daytime talk show where people are just celebrating the misery of others and using this type of test as the grounds to do so. If you ever watched those shows, I admit I may have seen 1 or 2 in my life. You don't need a polygraph fail in order to suggest that those people need some help. So the test is horrible, not a good measure. All right, number 7, one of my favorite problems here. So you have a shipment of microwaves, and there are 10. So I want you to picture 10 microwaves getting loaded onto a truck. The truck goes out for delivery. A restaurant gets 3 of those 10 microwaves, but here's the catch. 2 of the microwaves on the truck are defective. And we want the probability of at least 1. Well, probability of at least 1 means 1 or more, right? Well, that means I would need to know the probability of 1 being defective plus the probability of 2 being defective. And then 3, the third one's okay, right? Or let's take advantage of the complement. The probability of at least 1 defective unit is the complement of no defective units. And this is actually an easier computation because think about what's going on here. No defective units. So there are 3 events that are going on, right? The event being taking the microwave off the shelf onto the dolly to be delivered into the restaurant. So when that delivery driver grabs the first microwave, how many good microwaves are there? Well, there are 8 good microwaves, right? Because only 2 are defective, and there are 10 total. And then this is times, right? Because think about it. No defective means the first one and the second one and the third one are all good. And when we are what we know, the connective and corresponds to the multiplication rule. Now, he's grabbed a good microwave. How many good ones are left now? 7. How many good microwaves are left? 9. And then when he gets down to the third microwave, he will have already taken 2 good ones, which means there are now 6 good ones left and 8 total. And so when you compute this, you get, let's see here. Times 9 times 8. We get 0.5333, okay? And so this is really the key right here, using the complement. Where did that come from? Well, again, let me just remind you. The probability of no defective plus the probability of at least 1 defective is 1, okay? And so we're finding this indirectly. All right, number 8. Discover credit card numbers are 16 digits, but not all are random. So you've got 16 digits. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Now the first 4 digits of a Discover card are 6011. If you throw your receipt away and someone takes it out of the trash, they will know these 4 digits, right? Take a look at a receipt sometime. You'll see the type of card you used, which would tell someone those numbers, and the last 4 digits of whatever that card number was, meaning there are only 8. So just from your receipt, someone knows half of your credit card number. Well, should we worry? Well, they're going to guess the rest, right? How many guesses are there? How many options are there for each of these? Well, there are 10 digits, right? So every one of these has 10 options. So the probability of actually guessing your correct credit card number, well, there's only one credit card number, right? There's only one correct credit card number. There are 10 to the 8 choices, okay? And so that's probably not gonna happen, right? I mean, that's very low chance. However, computer could run through that very quickly, right? If you just let a computer guess, it can run through 10 to the 8th options very quickly. So what have you noticed happens? Well, most companies say, okay, we're going to give you this many tries, and then you're locked out, okay? That's one of the reasons why. Yeah, the probability of getting it right on any individual random guess is very small. But if you can run through all the options quickly, you can overcome that small probability. So fortunately, we have security measures like that. All right, number 9. In a room of 50 people, at least 2 share a birthday. So this again, I know we did this before, but we're again going to use a complement, okay? So the probability of no shared birthday plus the probability of 1 or more shared birthdays is 1. And so the probability that at least 1 birthday is shared is going to be 1 minus the probability that no birthdays are shared. Now, no birthdays being shared. Picture going around a room of 50 people. The first person has 365 days to choose from. And any one of those they say will not be spoken yet. Now, the next person. So to have no shared birthdays means this person and the next person and the next and the next and the next all have different birthdays. So the first person has set a day. The second person now, there are 364 options to be different. The third person has 363 options to be different. And so on. All the way down, well, what's 365 minus 50? Well, 365 minus 50 is 315, but that 315 operates kind of like 0. So we're going to go down to 316. And Excel does this very easily. And I will even show you how to do this here. Let's jump over to Excel. And so I have 365, and then, whoops, equals A1 minus 1, what? Equals A1 minus 1. All right, I'm going to take this all the way down to 316. And then B will be column A divided by 365. All the way down. And then I'm going to do 1 minus the product of B1 to B50. 0.97. Isn't that remarkable? If you get a group of 50 people together, 97% of the time there'll be at least 1 shared birthday. Okay. All right. And now number 10. So to win the jackpot in a Powerball, the player must select the correct 5 numbers between 1 and 55 in any order, and in a separate drawing, the correct single number between 1 and 42. And so 2 things have to happen. So that's going to be the probability of getting the correct 5 numbers times, because they have to do both, right? Correct 5 and these are independent events, and the correct single number, okay? Well, correct 5, any order. So we're talking about combinations. 1 out of, well, we have 55 choices, we're choosing 5. And then times the correct single. Well, we have 1, we're only choosing 1 number, and we have 42 choices. And so let's see what ridiculous low chances we have of winning. Okay. 1 divided by that times, well, 0 point. 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 6, 8. Probably not gonna happen, okay? All right, so I hope that helped. Nice little review of where probability started. Rework those, take a look at them, and I will see you guys soon.